So before we start talking, a couple things that you want to understand. So we talked about how to do filtering. So you have the center frequency, right? And you had this noisy signal. And let's say in the frequency domain, there's my version of noise. Okay? You get just all this junk, right? And the idea is you say, is there anything really there or not? And then you would put like some kind of filter, because you know what frequencies you're going to look at, and then you basically multiply these two together, kill everything off. Okay, so that's one way to do things. Now, a couple things to notice about this. First, I know where to look. Now, in a radar problem, generically you do know where to look. But in your dog problem, I'm not telling you what frequency to look for. You've got to find it. Okay? There's one other piece of information we haven't used here. Okay? The other piece of information we haven't used here is something about the noise itself. What did we say this noise was? We said this noise was white noise. Now, the nice thing about detectors is you can oftentimes keep resampling things, right? So, for instance, if I'm in that radar problem, right? Okay, that's my radar on top of a mountain, and there's your airplane coming in. All right, that's a really bad airplane. But anyway, there's my airplane coming in, or missile, whatever it happens to be, and I'm trying to get this thing. I'm continually taking information in on this. So I'm sampling not just once, not just twice, but I have a continuous sample stream. Okay? So I haven't made use of that at all in this filtering problem. So I want to try to think about how to make use of that. The fact is, when you have white noise, here's the specifics about white noise. White noise is random. And by the way, normally when it's randomly distributed, you say, well, okay, so how did I do it in my computer? I said, mean zero, unit variance. Okay? So when I add two pieces of noise together, they should be incoherent. If I had 3, 4, 5, 6, none of it should be coherent. In fact, I add a bunch of noise together, and I take its average, and its average is 0. Awesome. So I did one sample. What if I took a bunch? Then the idea would be that if I took a bunch of noise, then if I add all the noise together, it should be 0. And by the way, if it's not noise, it won't go to 0. So I'm going to use that to my advantage. But really, that's like to your advantage, too. Anything that's to my advantage right now is to your advantage. Okay. The only thing that's to my advantage and not to your advantage is maybe the homework. Because I already wrote it. You got to do it. So, okay. So we're going to try to work on that and see how that can work for us. Okay? So what I want to do is write another code today, building upon what we did last time, with the aim of kind of exploring this idea of what noise does. Okay? So I'm going to turn the lights down in front. Now, you guys in the back there, the TV screens, what do you got there in the TV screens? Xiao, can you see my computer? All right, great. Okay. All right, so here we go. We're going to start off with a little bit of code we had last time. So here it is. Let's just go through it again. You'll be writing a lot of code like this in your homework, first homework, for instance. And, of course, hopefully everybody likes these commands, clear all, close all, CLC. This just starts us off on a fresh slate for the code. And then here, I define a time domain. So I'm going to sample my signal for 30 units, whatever that happens to be. Let's say call it seconds. I'm going to sample for 30 seconds. And what I want to do with that 30 seconds and see what's in that signal. So I get to have a certain number of points I'm going to sample with. So here, there's 512 points in 30 seconds. So I sample at that rate. Okay? And now I can define my time interval as well as my frequency components in that sampling. So here, this T2 and T, so remember the lin space, the linear space, it goes from negative T over 2 to T over 2, so it's like negative 15 to 15. And I break it up into 512 plus 1 points. So 512 points plus the last point is the same as the first. It's periodic. Remember, I'm using Fourier modes, Fourier coefficients. Those are all sines and cosines of 2 pi periodic. Okay? Whenever you use Fourier components, assumptions, periodic. So I got periodic, and I throw away the last point by just taking the first 1 through n here. So t is what I really want. And then I define my wave numbers or frequency components. The 2 pi over t is there because the FFT thinks you're working on a 2 pi periodic domain. So this is a rescaling. And you go from 0 to n over 2 minus 1 and to minus n over 2 to minus 1. These are like my cosine 0x, cosine 1x, cosine 2x. And they're integers. And why do I order them this way? Remember, the FFT shifts things. Okay, it does one of these. So you got your Fourier components. When you do the FFT, it does that. Take a knife, cut it in the middle of the domain, switches it over.
So is Ks just minus n over 2 to n over 2?
Yeah, so when you do Ks, yeah, then I take away that shift, and now it's just from negative n over 2 to n over 2, but with the 2 pi over t factor in front of it. Okay. Now I'm going to define a function, such, and its Fourier transform, ut. Okay? So we have everything we got. We got a function, we have its Fourier transform, and now what we want to do, and let me bring this up a little bit. So there's my function, such. There is its Fourier transform, and I'm going to add some noise. There it is. So I take some, this is just going to be some coefficient. It's going to control how much noise I want to throw on this. And notice the way I put white noise on. You put it on the frequency domain. White noise is a collection, right, of white noise is all colors, right? So there's also a thing called colored noise, which is if you have certain frequency components that have noise in it, well, around those frequencies or colors, you would add noise there. But if we do white noise, it's all frequency components have noise. Okay? So what I do here is I go to every frequency component and add a random variable. This is rand_n. Mean 0, unit variance. Okay? And I add both a real and imaginary part. Just to my signal. So I've modified my signal, made it not so nice. Yeah?
Could you explain one more time why you need to add the imaginary noise as well?
Yeah, so if you do not add this imaginary piece, what you've added only is real components into your noise. It makes it symmetric. Remember, when you think about your frequency components, it's e to the I. When you do a Fourier transform, it's e to the I, whatever the frequency component has to be. Well, if you only add e to the I with real component, then what happens is, right, you're saying, okay, I'll add e to the I, but then e to the minus I looks the same. So what ends up happening, you end up at symmetric noise. You don't want to do that. And if you only add the imaginary parts, you add asymmetric noise. So you add both to get, so there's no correlation between the cosine I omega terms and the cosine minus I omega terms. Both of them get different noise. Okay? All right, good? All right. I'm doing a lot of this Hawaiian thing these days. I don't know why. I just developed it in last quarter where I was doing a lot of this. The little shocker, you know. So if you see a lot of that, I mean, I don't know what that means. Except I think maybe I'm having a good time in class, yeah? Oh, that's not so good. All right. We'll see how long that lasts, but I kind of like it. Hawaii made me think of the sunshine. That's a good thing to think about. Okay, so then I have my new signal, UTN. Can you guys still see my screen back there? Or is that me? There we go. Perfect. All right. U of n. U of n is my noisy signal. So let's plot these just to take a look. So, you know, we'll subplot them. Subplot, oh, by the way, see, I also want to, remember I have this K of S here. That's a shifted version. I want you to just remember that I've already done that. So I'll make a subplot of 2 rows, 1 column. And first we're going to plot the original signal, T versus U. And we'll plot that in red. And then we'll plot this noisy signal, T versus absolute value of UN. Plot that in black. And then in the second subplot, we'll plot, first of all, we'll plot the nice spectrum, which is Ks versus the absolute value of UT, which is the transform. Oh, by the way, FFT shift of UT. And we'll plot that in red. And now we'll plot the noisy part, which is Ks versus absolute value of FFT shift UTN. And I think, there we go. All right. So we'll just plot what these things look like. Here they are. Okay. So the red is my clean signal. The black is my muddled signal because it got polluted with noise. The red is my nice clean spectrum. And all that blue is the fact that I added noise at all these components. So normally what you're going to read from your detector is the blue.